Human Machine Interface, or HMI, written and presented by me, Jean Le Gouy. Here's the legal stuff. Okay, when we're looking at control systems, the window to the plant, the screen that we look at, is generally called a SCADA system. SCADA stands for, well, you can see it on the screen, so read it. What it doesn't mention is that it also takes care of the alarming. Things that go wrong that we need to tell the operator about. When we get alarming wrong, things go very, very wrong. For instance, when all the alarms suddenly went off in the control centre of the 3 Mile Island nuclear power plant, the technicians went into sensory overload. Essentially, they went into shock. It was as if someone had let off a flashbang grenade. Unsure what to do, where to start, they did nothing. So to understand how we perceive things, let's have a look at the human eye, which is where a lot of the problems start. We used to believe that there were little brain Oompa Loompas sitting inside the eyeballs, looking out through the eyes as if they were TV screens. But that's really not the case. This is how the eye actually works. Firstly, the first thing to realise is that we mostly see in black and white. The only part of the eye that sees actual colour is the fovea, the central bit marked there. Hold out your hand at arm's length. Look at the nail on your little finger, the nail on your pinky. That is the only bit that sees colour. The rest is a false image that was generated by your brain. Everything apart from where you're looking at your fingernail is in black and white. So, how does the eye see? Well, you look around the room, and the first thing the brain does is it finds all the straight lines and it draws them in quickly. Then it finds all the outlines. It looks for contrast in colours and shade, and it draws all the outlines. Then what it does is it colours in all the little boxes it just created, just like somebody painting by numbers. It decides on the colours partly by sampling using the fovea, the central part which sees colours, and partly by memory, because oranges are orange and grass is green. Then once it's coloured everything in, it does the shading. Mostly it does the shading by guesswork and decision making based on perspective. Now, what do you see? What can you see? So far as the colours go, we can see in red, blue and green. There's nothing magical about having 3 primary colours. Other animals see different primary colours. Goldfish, for instance, see 5 primary colours. It's not as simple as taking the luminosity levels of the 3 primaries, because red is so much more important than blue and green. If we see red, it actually dulls our ability to see the other colours. The colours we see are either due to a glowing object or light reflecting off something. When light reflects, the colour we see is due to 3 things. Firstly, the light source. Next, the level, the surface that it's shining on. And thirdly, our eye itself. You probably already know that things look different colours under different lights. Under sunlight or fluorescent lights, for instance. Also, things look different morning and evening. That's due to changes in the light source. A shiny surface can look totally different from a matte surface, even if they're the same colour. In addition, the light sensors in our eyes, which are called rods and cones, the rods see black and white and the cones see colour, well, these rods and cones are actually modified skin pressure sensors, and they still react to pressure changes. The eyeball itself is pressurized. It has to be in order to keep its shape. And small changes in the pressure inside the eyeball, due to things like stress or fatigue, can make things look totally different because it affects the pressure sensors, which are also the light colour sensors. Then there's the fact that your eyes just deceive you. Look at the cross in the centre. After a while, you can see a green dot going round. There is no green dot. It's just your brain putting it there. Now, remember I said that the eye shades by reasoning rather than observing? Well, have a look at the picture on the left. The orange dots are both the same colour. They are identical. But the brain is saying, oh, no. The one in the darker grey square is obviously darker than the one in the lighter grey square. And it colours it differently, even though those two dots are identical. The graph on the right shows how the eye responds to the three primary colours. Now notice how the red graph goes negative. That's where it's actually dulling out our ability to see blue and green. Also notice how the red graph peaks right about the colour of blood. There are two ways that colours can be added together. Additive colour mixing. That's what you get if you have three glowing objects. For instance, three different light bulbs with dimmer switches on them. When you change the colour of the light bulbs, that's additive colour mixing. The other type is subtractive colour mixing. That's when we're mixing paint. When we're talking about subtractive colour mixing, there are actually three different primary colours. And the three different primary colours are cyan, magenta and yellow. When we look at a screen, our eye starts at the top left. Then it scans right the way to the top right, and then it scans down the right hand side of the page. We do that because that's the direction that we read in. Anything that's on the bottom left is largely ignored. When people started studying colours, they realised that there were two sets of primary colours, the additive and the subtractive, and they're actually complements of each other. So they are called the primaries and their complementaries. Here is a demonstration of the primaries and their complementaries. When we see a primary against its complementary, it really stands out. In the 70s, the US Navy researched the best colours for computer displays in order to have things really stand out. The colours they decided best were blue and green. So they made a lot of displays with important things shown with blue on green or green on blue. Here's blue and green on blue. The only problem with this is it makes you sick. It literally makes you seasick to stare at blue on green or green on blue. The eye doesn't like looking at it, so tries to look away. And in that effort to look away, you get seasick. Not a great thing on a ship. Some other colours that we take as standard. Start and stop. You have two buttons that will start and stop the machine. One of them is green and one of them is red. Now, most of the world agrees that the start button should be green and the stop button should be red. Most of the world. In the US of A, there is a school of thought that says that the red button should start the machine because it makes it dangerous. And the green button should stop the machine because that makes it safe. It seems pretty dumb to me, but different ways. These are more or less the colours that people have largely agreed on. Red, danger, stop, prohibition, bad things. Yellow, that's caution, risk, danger. Something that's risky. Green is safe. Blue is normally a mandatory action. It's also often used as a colour for entry. Things can be in blue are often things that can be entered. Standards are always a problem. They seem like a good idea to have everything the same, but sometimes they end up being a big problem. On the left is a graphic that was designed for a water system. On the right is the standard that the customer was working to. Obviously, it was designed in the 1970s. Now, despite the fact that the left hand is clearer and easier to read and easier to interpret and just prettier, the customer went with the right hand one because that's his standard. So that's an example of standards actually holding back progress. Okay, things that are good practice. Right, I'll take a deep breath and start. Firstly, background. Muted tones are good. Light grey is a good colour, for instance. Secondly, if you're going to break up the screen into different parts, shadowing is recommended as a method of subdividing a display. It makes it have a 3D look to it. Background graphics should use muted tones, no alarm colours, so nothing red, nothing yellow, nothing bright. Use black outlines to highlight an object so that when you have the mouse hovering over an object, a black outline appears to say that's now, you're over that object. Font-wise, use fonts without serifs. They're the little flashy bits you get on letters. For instance, the serif on an I is the bit on the top on the bottom. So without serifs, it makes it clearer. Arial is the best example of this. Text size needs to be large enough to read. Never mind trying to get tons of information on the screen. Less is more here. Any more detail that you need, you'd put onto a pop-up window, so that when you hover over something, it might come up and say, well, this is the peanut butter additive mixing machine, or whatever. But you don't put all the stuff on the screen. System alarms status should be visible on all displays. So if you have a big alarm that comes up and says, nuclear reactor about to blow up, you really want to have that alarm visible on all of the displays. Alarms data should be displayed across the top, because remember you scan along the top. Alarm colours follow the conventions. Red is alarm, yellow is warning, green is okay. Flashing of an unaccepted, so if there's an alarm that's current and not being acknowledged, that the operator hasn't seen it yet, then it should flash and carry on flashing until he sees it and clicks on it to acknowledge it and say, yes, I've seen that now. Sounds are a great method of making you see alarms, but remember, too much sound, too much noise, and we go into sensory overload again. So any dynamic data, anything that's changing, should be along the top of the screen. Remember, that's the area that you scan. Or centrally and lower right. They're the important bits of information. Things should be grouped logically onto the screen. So the tanks that disperse should be together. You don't have one tank on one side and the other tank on the other, unless there's a good reason for doing that. Units should be given if they're useful And if they are useful, they should be obvious. So if it's a temperature, it should say degrees Celsius, so that somebody coming from America or Liberia doesn't think it's degrees Fahrenheit. The amount of decimal points is important. If you display a temperature as 546.453 degrees Celsius, well, there's so many numbers there, you don't really catch on to the fact that it's 543 degrees Celsius, which is bloody hot. If you're using green and red as running and stopped, then to prevent any confusion, actually write it underneath, run and stop. There should be navigation buttons on the screen, and they should be large and easy to see, and they should always be in the same place on every screen, so that every screen has the same, what they call, look and feel. And lastly, everything should line up and everything should look pretty. If it doesn't look pretty, your eye looks away and then you don't see the detail. And with that, that's the end of this short lesson.